Hello, everyone, and welcome to today's webinar. My name is Solveig Ray. I am part of the technical sales team here at Cascadia Windows and Doors, and really happy to be here today. I'm just going to go through a few housekeeping items before we get into the content, as the last few stragglers join. But now is your chance if you need to hop up and get a beverage or whatnot. You have a couple minutes before we get into the AIA accredited content. So without further ado, today's topic, which hopefully you all know, as you signed up for, is a very punny title of Tackling Window Pane. So we just want to focus on windows as a good way to improve overall building performance and how that can benefit your project. So, but first, housekeeping. There is some technical support in the email that you would have received. If for some reason you can't get through to me in the chat functionality or whatnot, there is a phone number you can dial there. We will email out the continuing education credits automatically. And if you don't receive those, you can always contact us. Questions, there is like I mentioned, question functionality. I do have my wingman Pete here with me to help answer questions as we go along. We have a big group, so feel free to type those in as we go. And if Pete doesn't get back to you, we will have time for Q&A at the end. And for audio, highly recommended to use your computer so you avoid phone charges. So now that you've hopefully all had a chance to see my face, I'm going to pop off and maximize the view for the content here. So today's agenda, I will tell you a bit about Cascadia to get started, and then we're going to go into sort of why we're here and the impact of Windows on your building envelope performance. We'll delve into the design factors and some of the performance metrics around high performance fenestration, how that can give you some design flexibility by using high performance options. And then once you're in that world of high performance, how do you cost optimize your design? We'll go into some real world examples using high performance windows, and then finish off with a short section on commercial fenestration and performance that can be expected. So it's a really kind of high level view in some parts today, but if all of you can come away thinking about windows a little earlier on in your project, and then considering the highest performance as a way to achieve your project goals, I think that would be a win. All right. About Cascadia. So we are a manufacturer of high performance fiberglass envelope components, and those components being commercial fenestration, including window wall for high-rise multifamily, including window wall products, as well as residential, wide variety of operable types for residential applications, and Passivhaus certified products for all of these markets. On the right here is an image of our thermal spacer for cladding support systems. It's also a fiberglass component that's key to high performance envelopes. You can learn more about that in other webinars from Cascadia. About our company, we're founded in 2008, located in Langley, British Columbia. And our Universal Series product is the first window product that is certified, designed, and produced in North America. So we're very proud of that. Our key markets are on the west coast of North America, mostly everywhere from Alaska down to California. And we focus on fiberglass as a material to enable us to accomplish our mission of achieving cost-effective solutions to meeting building energy performance standards that are becoming increasingly more stringent. So, first of all, what are building energy performance standards and why are they changing? Why are codes changing? Let's talk about that. So the big problem, of course, is climate change. It's here, and buildings are a huge contributor. You can see the 44.5% of CO2 emissions there on the slide. That's no joke, and regulations are changing to fix this problem. And just to illustrate, the problem a little bit more here. I've got an example. I'm going to show you 3 buildings here, all that range in construction time frame from 30s to the modern age, and they have all been retrofit. So they've all had a performance model or an energy model done to them to determine the effective R value. So when you think of R value, for those who aren't familiar, it's the measure of the resistance to heat loss of your material or your assembly. So, you know, a single pane 1970s aluminum window will have an R value that's less than 1, whereas a modern wall assembly is trying to achieve, in our climate here on the West Coast, about an R of 15.6. So just to give you the feel for that, I'll show you these 3 buildings. So as you can see here, there's a spread of 70 years from the oldest building to the new building. And so if you guess in your head right now, what would you expect for the R value for any of these buildings? Naturally, we would expect them to increase over time. However, that is not the case. All 3 of these buildings have R values between R2 and 3.5, which is frankly terrible. It's about the same as a fur coat. So, and sadly, the performance has actually gotten worse from this building to this building. So we have not done a great job of regulating our buildings to achieve whole building energy performance over time. And so this is where building energy performance standards come in. So in order for these changes to happen though, and for regulations to be enforceable, we have to have the technology there in place, ready to create the buildings that are being regulated. So, you know, manufacturers like Cascadia are creating these products to enable more stringent codes. But this is not, you know, this is mostly focused on new construction. However, things are changing for the existing building stock as well. You can see here on the right, the trend in New York here is to have the building energy performance evaluated and then rated and then taxed based on how well that building performs. So this is not just a trend in new construction, this is everywhere. A snapshot of a great example of a building energy performance standard is the BC Energy Step Code, which you can see a screenshot here from the design guide. And how it works is basically you have different levels of energy footprint over time. You have going to an increasingly more stringent energy footprint up to the last step here where it is net zero ready. You may have heard net zero ready referred to before. It's simply a building that has such low level of energy consumption that it has all of its energy needs are met by renewable energy available on site. So that's the net zero goal of most of these building energy performance standards. It's very similar to passive house. Some of you may be familiar with the passive house standard, and we have another webinar focused on that specific topic. In any case, what these building energy performance standards, this method reveals is the weakest links in the envelope, and which is why more attention is being paid to windows more recently as a weak link. What you're looking at here is a very simple kind of simplistic illustration of different envelope contributors to heat loss over time. So you have a sort of normal modern building code envelope here with walls, roof, and windows, and then changes to those different pieces of the assembly, how that affects heat loss. So, you know, between a passive house level envelope to one that has triple pane windows, there's a massive amount of heat loss here that is saved by improving the windows. So again, just highlighting why windows are such an important part of this story. So about 30 to 50% of your building's heating and cooling energy is lost through the windows. And more importantly, 20 to 30% of the window area for heat loss is the frame. And so naturally, by improving that frame, focusing on that, you're going to improve the whole window and by extension, the whole building. There are many jurisdictions that have realized this type of path for achieving real energy savings in buildings. And so they're incentivizing project teams to pursue these higher performance paths, a building energy performance approach, whether that be passive house or other. And everything from increased floor area allowances to alternate and additional funding and financing options, it is spreading. So to give you a bit more detail on how these types of standards work and how they're different from a normal building code that you may be familiar with, let's just use a visual here. So our typical prescriptive energy code, you look at this building on the left, takes the different assemblies in the buildings. You basically have a list of what you need. It's a recipe. They're all dictated completely separately. There's no attention paid or very little to how those different assemblies interact with each other to achieve overall building performance. Now, a building energy performance standard, such as Passive House or the BC Energy Step Code, they look at your building energy consumption for the entire year. You get an energy bucket, and depending on how much energy is leaking out of your bucket will determine what's left over to use for other things, other design elements for your project. So, and as that energy bucket shrinks, of course, that becomes more difficult, and all of the assemblies have to become higher performance. So it's really a totally different approach, and an energy model is required to achieve these kinds of standards. So I'm going to illustrate the impact of windows on this kind of an approach just by doing a quick demo on our website. So I'll hop out of the presentation. We're going to use sort of a mid-rise building as our example, and to put this in perspective, for our current building codes for most parts of BC here, an energy modeler will tell you to target around or a greater than R8 for your effective R value of that building if you want to have a chance of meeting the currently modern code. So let's start with a window to wall ratio of about 1 to 2 and get going into the calculator. So if you just go to Cascadia's website, we have a tools section here. You go to the R value calculator. It's a very simplistic weighted average calculator. Hopefully everyone can see it as well. We have our R value of our assembly on the left here, and the percent area that it takes up in the assembly. Walls, windows, and we're going to add a roof. So we said 2 to 1 walls to windows. So let's put in 60%, 30%, and then the rest will be the roof. Now, I mentioned earlier, a typical ASH rate 90.1 wall R value for modern code is going to be 15.6. And then our roof, I'm going to put in, R28, which I think is kind of normal. And then our windows, you take a current modern thermally broken double glazed aluminum window, you're going to be at around R2 to 2.5. So let's go in the middle. Now, you see down here, our total effective R value is 5.7. So that's still, a heck of a sight better than those retrofit buildings we were looking at, but we're not going to meet our targets for our project of R8. So what can we do? Let's increase the wall insulation. Let's make it 10 times thicker. Oh, gee, okay, well, that only got us to R7, so that's not very realistic. We're not going to increase the thickness 10 times. How about the roof? Let's add some there. Well, the roof, you can add infinite insulation to the roof, and because it's already a great assembly, it's not going to get you much. It's already at the point of diminished returns. So I'm obviously leading you to the windows. If we take this aluminum window and simply swap out the aluminum for a low conductivity material like fiberglass, we're going to get about R4. Bam! Look at that. We're meeting our target. So, so that's great. Well, then what happens if we reach further? Let's go to triple glazing and see what that gets us. So the R7.1 for a basic fiberglass triple glaze system. We have R12. So we're exceeding our target. saving a lot of energy. This is our spare energy in our bucket. What are we going to do with it? Let's maybe make our building more valuable by switching around the glazing area to the opposite. So this is going to be a completely different looking building. We're meeting our target, increasing the value of our building, and then we can also do other things like, reduce the thickness of the exterior insulation or things like that may be costly over the entire building. So hopefully that made sense. I'll pop back to the presentation now. Awesome. And here's just an illustration of the same concept. So with a real building, and this is based on an actual model done by RDH for us. So here's a typical residential building with 40% glazing ratio, and you can see the energy step code targets down here, the energy demand intensity and the energy use intensity down there, this building of 35 and 111. So just by switching to a fiberglass window wall system instead of aluminum, you can increase the glazing ratio dramatically and still reduce your energy consumption. So just a visual representation of that. Okay, so just to make sure everybody's had their coffee and still awake, and to help me get to know you a little bit better, I've got a poll question here. How familiar are you with fiberglass windows? So is it your first time? Do you know a little bit, but you've never actually used them? Have you specified them before? Or do you already love them and you're just so keen you're coming back to learn more now? You use them all the time. Thanks to everybody who's already answering. It's always nice to know your audience is awake, paying attention. All right, give you a couple more seconds there. Answers are still coming in. Okay, thanks. So it looks like there's a few newbies in the crowd. It's a good mix. A lot of people that are fairly new but familiar, so that's great. Thanks everybody for sharing. This next section, as you may guess from my question, is focusing in on fiberglass. So why does Cascadia focus on fiberglass? Why is it a great material for high performance windows? We'll start with how it's made and some of the materials properties. So it's the lineals are produced through the process called Pultrusion, where basically the glass strands are combined with a resin and pulled through a gently heated die, and out of the other end pops the lineals, which are then painted. So this is that process here. You have the resin strands pulling through the gently heated die, and out pops the extrusion. In this case, this is our fiberglass thermal spacer, but it's essentially the same process for the windows. Now, an important thing to note about this process is it is a thermoset process. So this resin, nothing's being melted here with temperature. It's a chemical reaction that is happening, and the die is just gently heated to assist to speed up the curing process. So it's a really low input energy process to produce this, and it's also very hard to undo it. So you're not going to have your material is not going to be susceptible to melting or creep caused by temperature change. I'll go into a little bit more of that. So the composite that comes out the other side is a very strong and durable material that lends itself to commercial applications. You have a material that's 10 times stiffer than a traditional vinyl window, so similar to aluminum. Also, that thermoset property I was mentioning just really makes it an inert material and a strong composite, which allows it to withstand extreme temperatures. So one of the reasons you see fiberglass selected for northern applications or extreme heat and extreme cold is it's very resistant to temperature fluctuations. And then of course, extremely durable because you can't really unfry the egg, so to speak. It's a very durable material that has a modeled lifespan exceeding 50 years, so which plays into the energy efficiency. Just really dialing in a little bit more on the materials characteristics. we have something called the thermal expansion coefficient. This is a really important detail that's often overlooked that plays into durability. So we have, what I'm showing you here is the glass, your glazed unit in your window, and the different frame materials that we typically see: wood, fiberglass, aluminum, and PVC. And this is coming out of the factory the day that it's assembled. Everything is in a neutral position. And then, excuse me, on the hottest day of the year, everything is going to expand at a different rate. So here you can see. And then likewise, on the coldest day of the year, everything will contract. And so in the case of, aluminum and PVC, you have a 3 to 6 times more expansion and contraction than your glazing unit. And why this matters, why do we care, is because your window is a system that has to maintain its performance over the lifetime. And there are seals in there, and different materials. So imagine the stress happening as those materials shrink and expand between all the joints and the seals, in particular between the glazing unit and the frame. So if you've ever seen an old window with the seal popping out around the glass, that's likely the blame. Another comment here, just to note, you see wood and fiberglass are very similar. So they are in terms of temperature, but another thing affecting wood is humidity. So wood changes dramatically depending on the type, based on the relative humidity of the air. So just a note there. The next characteristic, which is key to window thermal performance, is of course conductivity. So think of these circles I'm showing you as the holes in your bucket. You've got aluminum, steel, stainless, glass, PVC, fiberglass, and wood. So naturally, PVC, fiberglass, all these low conductivity materials are going to have a conductivity that's about 1,000 times lower than aluminum. So aluminum windows are fighting that in their design. So that the conductivity plays right into a critical characteristic of windows, which is condensation resistance. So never mind kind of the details of what this means. The condensation resistance shown here is an NFRC number. It's unitless rating of how well the window resists condensation on the frame, which of course is a big concern for hygiene and your health of your envelope. So going from a typical aluminum frame to a fiberglass frame, you're going to get a massive improvement there. Back to the topic of durability and low input energy. This graph that you're looking at is the lifetime energy consumption for different frame materials. So from straight out of the factory, you can see fiberglass has a low amount of energy to produce it. The others slightly more, but the bigger consideration is how that lifetime plays into the replacement costs of replacing those windows repeatedly in the future, and it adds up. So there's a similar discussion to be had here around cost as well. First costs versus replacement costs, and you'll find that the durable fiberglass has significant savings in that conversation as well. So what do all of those things combine to get you in terms of the window performance? Like I said a couple slides ago, windows are a system. You can't look at any of these characteristics in isolation, but they all come together to give you an overall thermal performance of the window. And a typical window these days for aluminum thermally broken, you're around R2. And if you switch to any low conductivity frame, you can expect around R3.7 for fiberglass, which is an 85% improvement in R value for that window. Now, Cascadia products, for reference, are better than this. We start out at R4.1 for double glazing and R7.1, which is a 250% improvement for triple glazing. So those numbers are used in the example. Now, one last thing I'm going to mention because it's important to our Canadian audience members, and it's also important consideration for high-rise construction, what we call non-combustible construction. is the sort of combustibility features of the windows. So this story begins because traditionally in Canada, or historically I should say, non-metal windows have been restricted in their use in Canada in tall buildings. However, it's only Canada. You know, everywhere else in the world, PVC and fiberglass have been used for a long time due to their economics and performance. And that has been like that way until recently. But now in Canada, the code has changed. So the National Building Code is now accepting fiberglass as a material that's suitable for non-combustible construction. But it was due to you know, a lot of work on the part of Cascadia and other manufacturers in you know, proving that equivalence to the current code accepted solutions. And I'll tell you a little bit here about how that happened. But basically, it's going to be incorporated shortly in the 2020 NBC. And then, you know, as different jurisdictions adopt those changes, we'll see that being adopted in the next year or so. So what we did was 10 window manufacturers got together to do this S134 fire test. So a lot of fire. And really the goal here was to prove equivalency to aluminum. And here's what the test entailed. You had a blowout fire in an apartment with a 3-story facade, and the fire couldn't reach past the 5-meter mark. There's other metrics as well, like temperatures and these kind of things that were measured, but that was a real big pass-fail criteria there. So after an hour of burning, the fire was extinguished and then left to burn. So there's flame spread and smoke measured as well. The fiberglass system put itself out and was well below the 5-meter mark. So that's great. We were very happy. That's our technical director dancing there. So aluminum windows were also tested in this test, and it wasn't to compare to say one was better than the other. Again, the goal was to say, okay, both of these products passed this test. They're both equally safe for high-rise construction. So that was kind of the background for the code change. And the language now is, if you actually go into the code, for combustible materials, such as fiberglass, the sashes and frames are permitted if they are vertically non-contiguous between stories. So basically, if you look at this image here, this is a cross-section of a window, of our window wall. You have the fiberglass component on the top story, and then the slab is surrounded by aluminum and mineral wool, and the fiberglass picks up on the bottom. So there's none of the combustible material continues around the slab. It's discontinuous over the slab area. All right, let's move on to a little summary here of you know, acknowledging that Cascadia is a manufacturer of fiberglass windows. I just want to summarize here why we focus on this material for high performance products. So firstly, the original why is the thermal performance. It's a low conductivity material that has strength and stiffness similar to aluminum, allowing you to not be limited in the design of your windows. Again, that low expansion and contraction coefficient, which will ensure that high performance is maintained for the life of the product and the life of the building, ideally. Again, that plays right into the durability. That thermoset material is really inert. In addition to that expansion and contraction coefficient, you have a material that's not going to be affected by UV, temperature swings, organic degradation, insects, this kind of stuff. So really, overall, very durable material. And all of that combines to a key part of our mission, which is the low environmental impact with low energy input and low replacement costs. So altogether, this gives you on your project savings, not necessarily as you may traditionally think on the line item of your windows versus other windows, but on the whole project, it's going to give you flexibility. And we'll go into more of that. So firstly, you may be able to increase your glazing area, like I mentioned in the R value demonstration. Another important one that has been used several times on retrofit projects is impact on mechanical system. You can sometimes avoid upgrades to mechanical systems if you're retrofitting, or for new construction, maybe reduce the size of that mechanical system. So reduce your capital cost. If there's no condensation risk at your windows because they're high performance, you can move those heating elements away from the windows, reduce the ductwork, make it more efficient. And of course, that frees up usable floor space in the suites if you're able to do that. Additionally, reducing the insulation requirement. Sometimes you can reduce or eliminate the exterior insulation that may be required on your building, or in the case of really high performance buildings where you're dealing with thermal bridging details that may be expensive to deal with, you can eliminate some of those. On the installation side, often the performance of a triple glazed aluminum system may be in consideration, while you may be able to use a double glazed fiberglass system instead, which is going to be a heck of a lot lighter and easier to install and a lot less headache and often lower cost. So a couple of extra points that are kind of more retrofit focused that are less tangible is the sound and comfort improvement that you get by going with the highest performance windows. And of course, everybody benefits from having reduced future operating costs for the life of the building, and it is significant. All right, let's go into window design. So I'll talk a little bit about some of the details of high performance window design before going into the section about your envelope and building design. Okay, so and yay, another poll. Let's see what you guys think of as the most important characteristics for windows when you're looking. Okay, there you go. You should see that poll now. FIA certified, thermal performance, lifetime, service life, structural strength, or cost. Top 3. Awesome. See those answers coming in. You guys are on the ball. All right, I'll give you a couple more seconds here. All right. Thank you to everyone who voted. So, looks like a lot of people are fans of thermal performance and lifetime. That's great. Cost is, of course, as expected, one of the major considerations. So hopefully by the end of this, we'll have you thinking about cost a little bit differently. Okay. So when we think about window types, there's a few different types. Obviously, there's hybrids of these, but these are the major buckets that they fall into is wood, vinyl, fiberglass, and aluminum. And because of their properties and strengths and weaknesses, they tend to end up in different markets. So typically we see wood in residential primarily. Vinyl ends up dominating the residential and multifamily markets just due to cost, first cost, and then fiberglass is really able to cover everything from residential to high rise. And aluminum has dominated the commercial market until now. So there's no one window type that is going to be the best in every situation. You really need to think for your project, what are the specific design criteria that really matter? What are the deal breakers? So, I put together a little matrix here to just communicate that yes, performance is a matrix. There's a lot of different considerations, but don't focus too much on the dots here. You'll go cross-eyed, but aluminum and fiberglass, they have more dots. They do have some more capability just due to their material properties being a stronger material. So, however, you know, if your main concern is absolutely first cost above all else, it's going to be tough to beat PVC. However, if you're working on, say, you know, a passive house project or an long-term ownership type of a project, first cost may not be your most important thing. You may be more concerned about durability and lifetime cost, in which case, you know, you're going to be better off with fiberglass and aluminum. If you need a multi-story window system, you're going to have to get that from aluminum and fiberglass for window wall. So there's just some examples that may play into your decision making. Now, if you're looking at high performance windows, the highest performance windows are going to have a lot, or hopefully all of these design elements. This is what you'll see in a typical passive house certified window. And certainly, obviously, we're using the example of a Cascadia product here. So triple pane, it's going to be triple pane for the highest performance applications with low E coatings, and that air is going to be replaced with argon or krypton inside, and there will be low E coatings. You will have warm edge spacers. So this one is often overlooked. It's the weakest point of the window. You have, this is where the biggest thermal bridge is in your window, and that little spacer there will determine whether you get a cold spot here and really affect your condensation resistance. So for the highest performance applications, you'll have a low conductivity spacer bar. Multiple gaskets. We have an operable window shown here, so it's going to have multiple gaskets in order to create a good airtight seal and break up the convection heat losses that will happen in this cavity. You want an insulated frame. Obviously, no matter what your frame material is made of, you have to break that path of conduction from the inside to the outside with something, and the less air gaps you have, the better. To that last point as well, often weaker window materials such as PVC, in order to do larger windows, they will have reinforcing in those cavities that can be steel or some other higher conductivity material. So it's just a consideration to take into mind when you're looking at your windows. Multi-point locking I'm showing here. So the highest performance windows are going to be compression seal, and you're going to have multi-point locking to really get that seal for air tightness. And as I already said, the frame is the weakest part of the window in terms of heat loss, so you want to minimize the surface area of that frame for heat loss. So another key consideration is the performance level of your window. So once you've kind of selected your window type, you know, do we go with double or triple glazing? Do we want to go passive house certified? Let's start with something that most people are familiar with here. I'll use the example of a fixed double glazed window here, and you're looking at NFRC performance here. So a standard double glazed window from fiberglass window here with a stainless steel spacer, that is a warm edge spacer, will have R4.2. By going to a standard triple glaze fiberglass system, you'll have R7.1. So that is now up to a passive house level of performance for only, so you get a 40% less heat loss, 40% less heat loss from your window area with only about a 10% increase in cost. So it's really, you know, if you're doing those trade-offs, definitely something to be considered. When you're in the triple glaze realm, you know you need that high performance level. There is a range of performance up to R7.7 that can be achieved just by tweaking your glazing for about a 7% improvement and similar cost range. Another thing is window configuration. So when you have high performance window frames, those frames are highly engineered and they're very expensive. They're the most expensive part of the window. So you need to, A, take advantage of the strength and capability and make your windows as big as possible, and B, reduce the amount of frame to reduce that cost. So here's some examples of how you can do that. You know, typically we'd see this kind of a design on a residential building. Let's cut out mullions, make those openers bigger. and simplify. Also, we see a lot of this as well, little small punched openings. Combine those, make a bigger one, get rid of the mullions, make it way less expensive. And then again, increasing your window size here, getting rid of that horizontal. When you have a material that's capable of spanning these large sizes, make that opener bigger, get more fresh air, which is a big part of why you have openers, and get rid of the horizontal mullions and vertical mullions. Now this one is more of the same. Just wanted to point out that you know, a lot of designs we see horizontal mullion at the guardrail height to try and eliminate tempering on both panes to have savings there. It's the best bang for your buck is going to be to eliminate the framing member in every case. The savings that you get there versus the costs, the increased cost of tempering the full height is not going to be equal. So you definitely want to focus on the mullions. So now this next section will go into overall design considerations for your envelope. So first of all, one of the key principles for high performance buildings and building energy performance standards is air leakage. How the windows play into that is how they seal within the system. So you're going to see fewer and fewer sliding windows possible on higher performance buildings because that sliding seal is relies on a friction seal there. It's just not as good. If you imagine the hatch on a boat, the best seal is going to be in compression, like I already mentioned in the window design area. So why does it matter? Like I mentioned, building energy performance standards require air tightness as a measure of whether you've achieved your proper envelope design. So the building is pressurized and they measure the air changes per hour. And the windows, often a huge part of the envelope, contribute significantly to whether you're successful. The good thing is this air tightness is tested by the North American fenestration standards. The SNAF's certificate shown here. You can look at any window in North America and see whether it you know, passes the US or Canadian minimum leakage, but often also manufacturers will show the actual leakage rate here. And if it's not shown, you can just ask your manufacturer for that to know whether it's helping you achieve your air tightness goals. The next key concept for your building envelope performance is shading. So you have a lot, you need to optimize. The first thing is the orientation of the building. And this also plays into Passive House principles. We want to minimize the heat loss or unnecessary heat gains in the summer to avoid cooling loads, and also heat loss in the winter. And sometimes in Passive House, optimize heat gain to minimize heat loads in the winter time. So all of this can be done to a large extent by just playing with the building orientation. So we would want to maximize the south-facing windows, minimize east and west that get direct sunlight, and then ideally eliminate northern-facing windows. So, but every site's going to be different, and you may be limited what you can do. So once you've done everything you can from an orientation perspective, we're going to look at exterior shading. So where possible, put overhangs to block out that direct summer sun while potentially allowing winter sun to help you with your heating load in the winter. You know, the windows are the only piece of the envelope that allow you to control so many things, impact views and light and heat. They're really a unique component in that respect. Once you've done overhangs, then interior shading is a next consideration that can help. However, interior shading can help you with privacy and glare, but the heat gain is not going to really be helped here because it's on the inside. That solar gain has already happened. It's already inside the building. Glass coatings. So low E coatings, now this hasn't always been the case, but they are essentially cost neutral. It's a no-brainer to have low E coatings on your windows, and you can greatly control how much of the sun's energy gets in and stays in your building just by adjusting those coatings, and how much of that is heat and how much of that is light. So really important, and probably this should be one of the first considerations on your window design. So none of these things I talk about in itself, or rarely is it going to be able to address all of these considerations for shading, privacy, glare, and heat gain all at once. So you just have to think about, what combination of these things makes the most sense for my project can I do to achieve all of these things. Okay, installation. This is another critical part of modern building construction, and a place where your windows, it can make or break your window performance, is installation. So a topic I wanted to cover for you guys today is attachment. So many of you may be familiar with the attachment method called the nail flange. So you see it here on the left. It's a continuous piece of metal that's fixed to the window frame, and it's usually a set distance, in or out of the rough opening, and it allows attachment to the face of the building, and often it's part of the seal for the sealing of the window. Where strap anchors are shown here on the right, they're intermittent and are not part of the sealing system. So as you consider these two different methods here, I'll just go into why we may or may not want to use those by understanding first, how do buildings move? So a window attachment system has to accommodate movement because buildings move, and more so high-rise buildings than residential for obvious reasons. We have horizontal drift, and we also have vertical deflection, just with the weight of the floors. So naturally, wind and seismic loads create these, and then live and dead loads create the vertical deflection. How that affects the rough opening that your window's sitting in, it basically, horizontal drift turns your rough opening into a trapezoid. So and then vertical drift will squish the top and bottom of the rough opening. So imagine, if your window is solidly attached on all four sides, a window frame coming from the factory or whatever is not designed to change shape. You want your window with that nice piece of glass in it to stay square and stay attached. So how do we do that? First, we attached at the sill, and then ideally, we want our attachment to accommodate these two different types of movement. So let's look at this with the actual attachment types in front of us. So with the nail flange, here you have, this can be on 3 to 4 sides of the window. So always on the jambs and the head, and optional on the sill. But it's basically a fin here that gets nailed to the face. So you can see here as well how this accommodates side-to-side movement is with a slot, and up and down movement, again with a slot. So imagine when you're attaching this window, you're screwing into here. You have to get the tension, the pressure on that screw just right so that it's solidly attached, but then somehow still allows it to slide around. And you'll be limited to whatever the length of this slot is. So additionally, where you place the window in the rough opening is limited by where this nail flange is on the window. So you've got a set location for your in and out. And you'll see why that matters in a second. So strap anchors, you can see here, this is a design where the strap anchor goes into a slot in the window frame. So hopefully that now makes sense for the horizontal movement, how those strap anchors can just slide back and forth in the slot while still remaining solidly fixed to the rough opening via the screws. So same with the vertical deflection. They can also, as you can see here, rotate. So with that vertical deflection, the strap anchors on the top side can rotate in that slot with no impact or stress on the window whatsoever. So this is why strap anchors are primarily seen in commercial construction because this level of movement is necessary. Additionally, I think, strap anchors are going to be seen more and more for all building types. As we go to higher performance envelopes, exterior insulation is a key part of it. And the window needs to be as far into that insulation layer as possible. Now, this is a magical scenario where this window is held up by, sky hooks or something. There needs to be structure somehow under this window holding the weight. But the strap anchors, because they attach back here, allow you to push that window out into the insulation layer. This is a screenshot from the BC Step Code Guide, by the way. Okay, a few project examples. The last few minutes here, we're going to go through, give you some visuals on how high performance windows are applied. This is a project in Hamilton, Ontario. It's a Passive House certified Enerfit retrofit project. Very, very interesting project. There's a lot of case studies on this that you can see. Cool thing that they had to do to this project to achieve their goals was cut off all of these balconies that were massive thermal bridges. So you can imagine all of the structure exposed here is just leaking heat like crazy. So they did exterior insulation and then did triple glazed fiberglass windows everywhere. Got rid of the balconies, but in order to compensate for that, loss of exterior space, they needed to add Juliet balconies that were attached directly to the windows. So very cool here. This is, with the balconies all removed. And additionally, that concrete structure was exposed and just leaking heat. So they had, in order to accommodate the exterior insulation, they had to move the windows very far out away from the structure and designed a low conductivity fiberglass support here to support the windows and move them out. So very fascinating. Here's a little image of that Juliet balcony. These are full openers, so they could slide this, fully open this door and get their little, the balcony outdoor feel with that. So very interesting project. Next one here is 825 Pacific, again, a Passive House certified building. They did a combination of, again, pushing the windows out here and exterior insulation with thermally broken cladding support with triple glazed windows. And here's that building all finished. This community college in Oregon used fiberglass windows double glazed as an option to get equivalent performance to a triple glazed aluminum system with the cost savings and installation improvements that I mentioned previously. So see some pretty big, large awning windows there. Simplify the design, fresh air. The Chelsea, this is a Vancouver project, the first installation of fiberglass window wall. And as you can see here, the unitized window wall system going in. And this, again, the double glaze fiberglass system enabled the project to avoid some other costly energy improvements to mechanical systems and things that they were considering in their design. Here's the outside look. Okay, so I want to leave a few minutes for questions. So I'll just quickly go through the commercial glazing here. So, fiberglass window wall was invented to bring super high performance, passive house level performance, typically only seen in residential systems, to the high rise market because there's such a need and it just makes sense. So here's a quick look at what a fiberglass window wall looks like in that bypass area where we have an insulated slab bumping up your performance from a traditional aluminum system. So what you can expect from a fiberglass window wall in terms of performance areas for the vision glass, this is the same as the windows I showed you earlier. It's R4.1 to 5 for double glazing. For triple glazing, R7.1 to 7.7. And then for that bypass area, typically aluminum window wall is like R2 or R1 for the slab bypass. So this is a major improvement here. And then of course the back pan area, which is the wall part, you get a 16. So again, same image we saw earlier. This is what fiberglass window wall enables you to do on commercial projects, is go from this to this. Okay, so with 5 minutes to go, as you all type in your questions, I'm going to bring Pete back in so he can field the ones that didn't get answered or that everyone would benefit from. And I'll just leave you with 3 takeaways here in a different order. We have, so obviously windows have a huge impact. They're the weakest link. They should be thought about very early on. Pay attention to the product details. There's some, tricky things that can make or break your project. And an energy consultant or envelope consultant will help with that process. Also, high performance equals high flexibility. So shift your thinking from the individual cost of the line items on your building list to how does the cost as a whole get impacted by using high performance components. So with that, I will open it up for questions. Thanks everybody for sticking through to the end. Okay, Pete, are you there?
I am here.
Yes.
Your first question is on slab deflection requirement for your Windows system. Do you want to take that one?
Slab deflection requirement to offer a deflection channel. Okay, so there are two options, I suppose, with our window products. You have the standard universal series, which is for punched and strip windows, and then when you go to window wall, that deflection increases because of the design of the head components. So standard is plus or minus 3/8 of an inch. I guess you get about a 3/4 of an inch overall deflection, and then if you go to the window wall components, you'll get 1.5 inches overall deflection. So hopefully that answers your question. All right. Pete, were there any other?
There were through the meeting. One that is often comes up is around cost. Cascadia obviously is typically compared to commercial grade aluminum products, in which case we are typically slightly more expensive than sort of standard window wall providers in places like the Lower Mainland, but a value engineered possibility against sort of higher end aluminum, high thermally performing aluminum windows out of Europe. We're typically about a 15 to 20% cost savings against the likes of Schuco or Rayco. And then against vinyl, obviously we're significantly more expensive material cost, but our product will last 2 to 3 times longer than a typical vinyl window. So when you factor in the life of the building cost, Cascadia is a higher value.
Yeah, there was another one I saw here about flexibility. Yeah, sorry, I didn't touch on that during the matrix slide. My intent on the flexibility dot was just around shape. So if you have any funky shapes, like if you need a round window, fiberglass is not going to do that. If you imagine that pultrusion process, it doesn't really, it lends itself more to straight shapes as opposed to curves. So that was that one. All right. Okay. Still a lot of people on the line, so if you have any other questions, pop them in now. Maybe while people are Yep, we can get a PDF of the presentation. Thanks, Julio. I'll quickly. Okay, some more questions coming in. Great. Are there any Windows shading devices available to integrate with your system? So no, the answer to them is no, and there's a good reason for that. Windows are designed to be Windows and open and just be as thermally efficient as possible, whereas shading devices are, put a totally different kind of load on the frame. It's structural. So we would, in any case, recommend a shading device be attached to the structure around the window. At the point when you customize a window to accommodate the structural loads from a shading device, it basically destroys the thermal performance. You end up having to put steel and things inside the window. So it's better to avoid that if you can. But of course, there's customization that's possible. External devices. Okay, I think I talked about that one. Percentage adoption by residential. Pete, what would you say that? Say for
we don't have hard numbers. It would vary by province and by state for sure. There are a lot of fiberglass window providers that are active in the residential space as well. Cascadia doesn't play in that as much as we do the commercial space, and the larger rough openings are where Cascadia is different than the residential focused fiberglass window providers, but it's definitely increasing rapidly as thermal requirements increase. So across North America, fiberglass is gaining market share from vinyl most specifically.
Another good question here from Marilyn. What is the maximum size of a fixed window wall you can accommodate? So window wall, or the size of any window is dictated by, the design pressure. First of all, how much wind load is going to be on it, because any spanning members have to resist deflection. So that's a key one. And in the case of the fiberglass system, we have a manufacturing limitation as well. That's at around the I want to say the 14 to 16 foot mark, where you have to have structure just for manufacturing reasons. So typically, at 12 feet you run out of glass and you have to put a mullion, and then at 14 feet you have to put structure. So it's really designed as a slab to slab kind of a window system. And if you have larger heights and spans, say continuous, like a foyer or something like that, then you would need to put in structure at approximately, every story or so to accommodate the weight, or to support the weight of the window system. Hopefully that makes sense. But someone at Cascadia can give you feedback on your particular facade limitations based on your location and the glass type you're looking at, these kind of things.
There's a question on hospital construction as well, and Cascadia has done several hospitals in British Columbia and others across North America. If there's a specific job that the asker of the question is working on, I'd be happy to discuss that with them, because we are a good fit for we're doing a lot of schools as well these days, and anything that's looking to hit above their standard weight on thermal performance. Obviously, in a commercial application, we're usually considered, and would be happy to talk to you about that project.
Daryl, I'm just getting on your question here about angles, coupling angles. So if you go to our website on the window wall page, there's a detail library of all the cross sections kind of standard with the window wall, and you'll see here that it shows gentle concave curve here for coupling. So the way that the windows couple in two parts here with a sort of an H-shaped extrusion and then two halves, it does accommodate some amount of angular alignment, I would say there. And we have done a project recently that has a big concave window in Vancouver, similar to this. So I can't tell you the exact angle here, but it's gentle angles like this that can be accommodated. Okay.
I think that may be, oh, still a couple more coming in.
Mm-hmm. Okay, James. We will ask them if, okay.
Thank you, Jim.
Yeah, thank you, James. What performance costs are coupling devices? Oh, performance cost or coupling devices. I assume you mean how does the coupling affect the thermal performance? If that's the question, then you know, these are the coupling devices. So all of the portion in here is the Universal Series fiberglass with foam insulated window, and then you have a small aluminum piece here, and this is the window wall extension here. Those are outside of the thermal envelope. So this is, you know, inside your building, so same temperature, and then this is outside. There's no thermal bridge there, so to speak. So it's specifically designed to have a negligible impact on the performance. Where performance is impacted is if there's reinforcing in this cavity, which can happen for large windows. There will be either fiberglass or steel in here. And you can see that with modeling that we've done. If you have a performance model that you need to put in those details, we can provide that information. All right. I think we're well past our 1 hour mark. So if there's any last questions, please type them in. Otherwise, feel free to reach out directly to myself or Pete. Anyone at Cascadia will be happy to help you guys. And do look up our other webinars for other interesting topics if this one piqued your interest. Okay, thanks everybody. Signing off.